After this video, you'll be able to tell, at a glance, whether a shaft is truly turning friendly just by looking at the drawing, because the wrong choice triggers the same chain on the shop floor every time. The first part looks fine, the second is borderline, the third comes back rejected. The operator keeps adding a bit more adjustment, in process checks explode, scrap increases, and in the end the issue isn't the part got expensive, it's that the delivery date slips. Today we'll look at turning not as can it be done on a lathe, but when it's the right choice, and when it makes costs blow up. Turning is built on one simple idea: the workpiece rotates around its axis, and the cutting tool follows a controlled path to remove material. In most setups you'll see two basic tool motions. The tool approaches in the radial direction, and feeds along the axis. That's why turning is extremely strong for rotational features, OD and ID diameters, shoulders, tapers, grooves, and faces. The same logic supports facing, straight turning, taper turning, grooving, cutoff, threading, and on many lathes, drilling and boring operations as well. Turning produces rotational geometry very efficiently. Off-axis flats, pockets, or non-rotational features may require live tooling or a secondary process. So when should you choose turning? 3 practical criteria. 1. Is the geometry rotational? If most primary surfaces are defined around a single axis, turning is usually the shortest path. 2. Does the function require a precise circular surface? Bearing fits, press and slip fits, and sealing interfaces often benefit from turning because it can deliver controlled, repeatable results. And what matters isn't only size, it's also how concentricity, runout, and surface finish affect function. 3. Do you need to re-establish a critical surface after a primary process? After casting, forging, or additive processes, turning is a very common finishing step to clean up rotational surfaces, true shoulders, or create a reliable datum. You can make the same part on a mill, but the real question is, how many clampings, how many operations, how many measurements? 3 key limits of this process. Limit 1, you must rotate the part and hold it securely. Mass, balance, and available clamping area become constraints. Per workholding equals runout and equals size drift. Limit 2, long, slender parts deflect and vibrate. Center support may be required. Cycle time and setup sensitivity increase. If possible, design it short and stiff. If not, plan the support strategy from the start. Limit 3, tight tolerances and better surface finish increase not only cycle time, but also measurement and adjustment load. Small offsets can show up quickly in diameter. Temperature, tool wear, and chip control quietly amplify variation. 3 typical mistakes. Mistake 1, vague edge break and deburr notes. On the floor, this often becomes unnecessary labor and inconsistent quality. Specify what's function critical and leave the rest to a sensible standard. Mistake 2, ignoring standard tool geometry in shoulders, radii and grooves. Sharp shoulders, narrow deep grooves, and hard-to-reach corners usually mean special tooling, extra operations, and more inspection. Mistake 3, designing features that create interrupted cuts. Slots, intersecting holes, and discontinuous surfaces increase vibration. Tool life and surface quality drop. Cost inflates silently. A quick turning DFM checklist. 1. Leave a work-holding surface. Define a stable reference area. If possible, keep the datum chain consistent across 2 operations. 2. Reduce long slender sections. If needed, incorporate the work-holding and support strategy into the design. 3. Use standard radii and chamfers. Reduce sharp corners and align with common insert nose radii when possible. 4. Avoid narrow deep grooves and poor access. Widen grooves, relieve corners, and reduce special tooling need. 5. Specify tolerances as tight as necessary. Every tighter callout becomes an extra control point and an added risk. On turn parts, the most common geometric dimensioning and tolerancing topics are circularity, roundness, and cylindricity, and when function requires it, runout and concentricity come into play. For measurement, a micrometer is the practical tool for diameter control, and an indicator is the fast way to check runout. We'll cover deeper topics: tool selection, cutting parameters, tolerance analysis, and fixture design in the advanced training. And if you found value here, Please like the video, subscribe, and turn on notifications so you don't miss the next lesson.